Hello, welcome. In the previous part of this lecture, we discussed vectors in Rn. In this part, we're going to talk about vector spaces. Let's begin our discussion with the motivation of vector spaces. In Theorem 9.1.1, 10 special properties of vector addition and scalar multiplication in Rn were listed. Suitable definitions of addition and scalar multiplication reveal that many other mathematical quantities, such as matrices, polynomials, functions, sequences, and many others, also share these 10 properties. Any set that satisfies these properties or axioms is called a vector space, and the objects in the set are called vectors. Let's have a look at the formal definition of a vector space. Definition: let V be a set of objects on which two operations, addition and scalar multiplication, are defined. If the following listed axioms are satisfied for every element U, V, and W in the set V, and every scalar C and D in a field F, then V is called a vector space over the field F. Property 1. If U and V in the set V, then their sum U plus V is also in the set V. So the set V is closed under addition. Property 2. U plus V is equal to V plus U. So the addition is commutative. Property 3. U plus V plus W is exactly equal to U plus V plus W. So the addition is associative. Property 4. There exists some element called 0 in the set V such that U plus 0 is equal to U. This should be true for all U in the set V. So this property is called the existence of the additive identity element. Property 5. For every U in the set V, there exists some element called negative of U such that U plus negative U is equal to the 0 element in the set V, which is also called the additive identity element. Property 6. For every scalar C in the field F and every element U in the set V, the scalar multiplication CU is also in the set V. So for every element U in the set V, the scalar multiple is also in the same set V. This property is called the closure of scalar multiplication. The set V is closed under scalar multiplication. Property 7. For any scalar C in the field F, and any two elements u and v in the set V, C times u plus v is exactly equal to cu plus cv. So this property is called the distributive property. Here, the scalar c distributes over the elements u and v in the set V. Property 8. For any two scalars c and d, we have c plus d times u is exactly equal to cu plus du. This property is also called the distributive property. Here, the element u in the set V distributes over the field elements c and d. Property 9. C times d times u is equal to c times du. This property is called the associative property for scalar multiplication. And finally, property 10. There exists an element 1 in the field F such that 1 times any element u in the set V is equal to the element u. This property is called the existence of multiplicative identity element. So, any set V whose elements satisfying all these 10 properties with the scalars from some field F is called a vector space over the field F. If we choose the field F as the field of real numbers, then the set V is called a vector space over the real field R, or simply a real vector space. Similarly, if we choose the field F to be equal to the set of complex numbers, then the set V is called a complex vector space. In physics and engineering, complex vector spaces play important role. In this lecture, we will only consider real vector spaces. Let's see a couple of examples of vector spaces. The set Rn is a real vector space. Certainly, the set Rn with the standard vector addition and scalar multiplication satisfies all these 10 properties we list here. In fact, these 10 properties are taken from the properties of the vectors in the set Rn. Let's see another example. Let M 2, 3 be the set of all 2 by 3 matrices over real numbers. To show that this set is a real vector space under the standard matrix addition and scalar multiplication. Let's have a look at the solution. The set M 2, 3 is a set of all 2 by 3 matrices where each entry in the matrix is a real number. So A sub 1, 1, A sub 1, 2, A sub 1, 3, A sub 2, 1, A sub 2, 2, A sub 2, 3 are all real numbers. We will show that this set is a vector space under the standard matrix addition and scalar multiplication. To show that, we will verify the first few axioms in the definition of a vector space, and the rest will be left as an exercise. To prove property 1, that the set M 2 by 2, 3 is closed under matrix addition, we take two matrices A and B in this form. Clearly, the sum A plus B is the matrix, which is exactly in the form of a 2 by 3 matrix. Therefore, belongs to the set M 2, 3. So, the set M 2, 3 is closed under matrix addition. Property 2. Since matrix addition is commutative, the axiom is easily verified. For example, if we take two matrices A and B as previous, then the sum is this matrix. In this matrix, each entry is a real number, and we know the sum of two real numbers is commutative. So the first entry in this matrix, A sub 1 1 plus B sub 1 1, can be written as B sub 1 1 plus A sub 1 1, and similarly the other entries. And by definition, this matrix is the sum of these two matrices, in short, B plus A. So we prove that A plus B is equal to B plus A. Matrix addition is commutative. Hence, property 2 is satisfied. Axiom 3. Since matrix addition is associative, the axiom is easily verified. So if we take three matrices from the set M 2, 3, we can easily show that this property is satisfied. A plus B plus C is exactly equal to the matrix A plus B plus C. Property 4. We take the zero matrix denoted by O, which is equal to this matrix, a 2 by 3 matrix with all the entries equal to 0. Then clearly A plus the zero matrix is equal to the matrix A. And this is true for all matrices in the set M 2, 3. Property 5. If we take a matrix A in this form, then its negative denoted by minus A matrix is defined as this. So each entry in this negative A matrix is exactly the negative of the entries in the original matrix A. Then clearly A plus the negative A matrix gives us the zero matrix in the set M 2, 3. Property 6. For any scalar C in the real field, C times A is defined to be the matrix whose components or entries get multiplied by the scalar C. Clearly, this matrix is also in the set M 2, 3 because it has 2 rows and 3 columns. In this fashion, we can prove the rest of the axioms. Hence, we prove that M 2, 3, the set of all 2 by 3 matrices with real entries, is a real vector space in general. The set M N, this is the set of all M by N matrices with M rows and N columns is a real vector space. If we choose the field F to be equal to the field of complex numbers, then we can show that the set M n is also a complex vector space. Let's have a look at another example of a vector space. Let P sub 2x be the set of all polynomials over R of degree less than or equal to 2, meaning that the set P sub 2 of x is a set of all polynomials of this form. For example, 2x squared minus 4x plus 5 is in the set. Negative 5x minus 7 is also in the same set. Here we can consider the coefficient of the term x squared is 0. So it is exactly in the form. But 5x cubed minus 3x squared plus 4x minus 2 is not in the set P sub 2x. Since it is a cubic polynomial, it doesn't fit in the definition we provided here of P2. Notice any constant 3 is also in the set P sub 2 of x, because we can consider this as a polynomial of the form a sub 2x squared plus a sub 1x plus a sub 0, where a sub 2, a sub 1, and a sub 0 are real numbers. We want to show the set P sub 2 of x is a vector space. Let's have a look at the solution. We take two polynomials, P of x and Q of x, from the set P sub 2, as shown here. Then P of x plus Q of x is given by this polynomial. We can simply get it by adding the coefficients of the same power of x. Now, if c is any real number, then c times p of x is given by this expression. Therefore, we see that the sum of two polynomials, p of x and q of x, is also in the set p sub 2, since this expression is exactly of the form shown here. Similarly, c times p of x is also in the set p sub 2 of x, because of the same reason. The expression of c times p of x is exactly the form in the definition of p sub 2 of x. So we proved property 1, namely the set p sub 2 of x is closed under addition, and property 6, namely the set p sub 2 is closed under scalar multiplication. Similarly, we can verify the rest of the axioms in the definition 9.1.5. Hence, p sub 2 of x is a vector space. Please try to verify the rest of the axioms. Next example. This example is from calculus. Let C A comma B, denote the set of all continuous real-valued functions defined on the bounded and closed interval from A to B, with A is strictly smaller than B. We can show that the set C is a vector space. Let's discuss the solution. We take two continuous functions, f and g, from the set C. Then from calculus, we know that the sum of continuous functions defined on a bounded and closed interval is also continuous. So, the sum function f plus g is in the set C. So we proved that the set C is closed under addition. Similarly, for any scalar C, the function denoted by Cf, it is the scalar multiple of f, is also continuous on the bounded and closed interval a to b. Therefore, the function Cf is also an element of C. So we proved that the set C is closed under scalar multiplication. To prove the property 4, we need a concept of the zero function. The zero function is denoted by 0 of x, which is equal to 0 for all x in the set a to b. So for all x from the bounded and closed interval a to b, the zero function gives the output, the scalar 0. Clearly, the zero function is a continuous function, hence belongs to the set C. In a similar fashion, we can verify the rest of the axioms in the definition of a vector space. Thus, the set C is a vector space. Please try to verify the axioms. Theorem. Properties of scalar multiplication. Suppose V is a vector space and V is an element or vector in the vector space. Now we have these four properties true. Property 1. The scalar 0 times the vector gives the 0 vector. Observe here, the 0 in the left-hand side of property 1 is scalar 0 from the field, and the 0 we see in the right-hand side of the equation is the vector 0 in the vector space. Property 2. Any scalar C from the field f times the 0 vector in the vector space V is equal to the 0 vector. Property 3. If a scalar C times a vector V is equal to the 0 vector, then either C is equal to the 0, the scalar 0 in the field, or V is equal to the 0 vector in the vector space. Property 4. The negative 1 in the field F times the vector V from the vector space V is equal to the negative V, which is called the additive inverse of the vector V. The proofs of these properties are exactly the same as in the theorem 9.1.3. Let's see a non-example. The set of integers z, namely the set of all integers z is not a real vector space. Note that the set Z is closed under addition. If we take two integers from the set Z, the sum is also in the set Z. But if we take a scalar C as 1/2 and an element 3 from the set Z, then the scalar multiple, the product C times the number 3, is not an integer. It's not in the set Z. So the set Z is not closed under scalar multiplication. So property 6 doesn't hold true for the set Z. So the set of integers Z is not a real vector space. Another non-example. The set of polynomials of degree exactly 2 is not a real vector space. Previously, we showed that the set of polynomials of degree less than or equal to 2 is a vector space. But now we say that the set of polynomials of degree exactly equal to 2 is not a real vector space. To show that, we observe that the set of polynomials of degree exactly equal to 2 is not closed under addition. For example, if we take a polynomial p of x as 2x squared minus 4x plus 5 and q of x as negative 2x squared plus 5x minus 6, then the sum p of x plus q of x is x minus 1. So the sum is a linear polynomial, not a quadratic polynomial. So this polynomial is not in the set of polynomials of degree exactly equal to 2. Hence, the set of polynomials of degree exactly equal to 2 is not closed under addition. So it's not a real vector space. With this, we end the part 2 of lecture 1.